Let's talk next about waves, ocean waves, and the effects that they have shaping shorelines. What are ocean waves? So they are undulations in the surface of the water that are caused because those waves are ways that energy of motion propagates through the water. In fact, those ocean waves are themselves caused by wind. Both winds near shore and many miles offshore can contribute. So it can be a still day on the beach, but you'll still see some waves because wind offshore is blowing harder. So that is, the waves don't necessarily stop when the wind gusts locally stop, because wind elsewhere is also building up and imparting energy on that water. We can describe the features of a wave by describing its wavelength. So if you go on a beach, standing on the beach and you're looking out, and you can see that there's a wave coming in, and then behind it is another wave coming in, right? And they're sort of stacked on top of each other, moving in this direction. The wavelength is just the distance between wave crests. We can also talk about the wave height, how tall these waves are. And lastly, we can talk about the period of the waves, which is the rate at which the waves are hitting in terms of time. So that would be something like waves per second or waves per minute. And we can describe with another equation, simple equation, the relationship between some of these. The wave velocity, the speed at which the wave is moving, is equal to the wavelength times the period. So wave velocity V, speed, velocity, pretty similar, is equal to wavelength, L for length, times period, capital T. Let's think about the units of that. What do we normally, velocity, we might have it as something like meters per second equals something like wavelength is meters. You might even say meters per wave to make this consistent. And then period would be waves per second. You cancel out the waves, and what do you see? You see you get the same units back, meters per second. So that's why it makes sense that if you took a length times a period, you would get a velocity. So when waves are moving, for the most part, like the water itself does move, but it's not continuously all of it moving onto shore. For the most part, the waves move towards shore, the energy itself moves towards shore, but the water making up the waves returns to its original position after each cycle. So you see some of the paths of the motions of what a water molecule might follow, or say, you threw like a floaty beach ball out into the water. It's not that the beach ball instantly gets pushed on shore by each of these waves, but rather it rides up and then down and then back up and down. And you experience this yourself if you go out into the water. The water itself moves in these circular pathways. Whereas the wave goes by, it rides up and over and then comes down when it's in the trough and then back up and over. And each of these particles follows this weird, surprisingly circular pattern as the wave moves past. It also turns out that most of the motion of a wave occurs at the surface. If you've ever been out in the water and waves are going over you and a big wave is coming, you know that you can go underneath them and not feel the full force of the wave. That's because most of the motion is right at the surface, and the motion gets smaller and smaller and smaller as you go down in depth. And a nice rule of thumb is that motion from the waves actually stops at about a depth of 1/2 wavelength. So for example, here's the wavelength of this particular set of waves. Half that wavelength is this length here. And that is about equal to the depth at which all the motion from the wave stops. So waves really only affect the water down to about half of their wavelength. We talk a lot about sediment in here, right? And we think a lot about how sediment gets moved by and in water. And so if we're thinking about shorelines and the way that the sediment is affected, we want to know how deep the waves are going to affect the sediment. Because they only work down to about half of their wavelength, they're only going to interact with the shore sediment down to that depth, which we call the wave base. So that's about as deep as the water is moving in response to the wave. So if you were to go down and look at the shoreline, you would see that the ocean bottom is sort of agitated and rippled by those waves down to a depth of about half the wavelength of typical waves on that beach. And as you go deeper than that, the ocean bottom is less and less disturbed by those waves until you get to here. And then under that, for the most part, those sediments are flat. Oftentimes you'll find a mix of siltier, finer sediment there because the waves are not imparting the energy to move those particles as much. So all this water down here is basically still water. Here you see a lot of that information summarized and a little bit more imparted, some names of areas. So the part where you are going to experience those waves piling up and breaking is called the surf zone, usually underwater. And then the part that is just above the waterline is going to be called the beach. I mentioned waves breaking because as the waves move and they get to shallower and shallower water, the water slows down as it drags along the bottom and starts to stack up on itself and gets higher and higher as you get near shore until eventually it's so tall that it topples over under the force of gravity and the wave breaks. So that area where waves can break is called the surf zone. And then that water falls over, it cascades up the beach in swash motion, and then it comes back down in backwash motion. So swash is up, backwash is back. So just to reiterate, why is it that waves grow in height as they approach shore? As they interact with the shore, they drag along the bottom. The whole wave actually slows down a little bit. And so it causes the wave to pile up on itself. Go from a wave moving pretty fast to a much more stacked wave. This is a big exaggeration, moving much slower. And then because gravity is trying to pull this down, it eventually will topple it. Some other features of waves as they're moving is that waves can be at sort of an oblique angle to shore, especially offshore. But as they approach and get closer to shore, right? If we're looking at it this way, so this is the left side of the wave and this is the right side. The left side gets shallower before the right side does. And as a result, the whole wave turns as it comes towards shore. What we call refract, right? The wave motion is turning and refracting as it moves toward the beach, so that even if wind is not blowing straight at the beach, the waves end up coming in relatively straight when they hit the beach. So that's due to wave refraction. It's because the part of the wave that is moving closest to shore first slows down more first, and it turns the whole thing. Here in this image, you might have wind blowing at some weird angle, but whenever you take a picture of the waves, you'll see that they are pretty much parallel to the beach itself because they have all refracted already, right? These are already broken waves. They've already broken. So you know that the water here is pretty shallow as it's coming onto this very flat active coastline or passive coastline here. Ooh, keep mixing that up. It's a passive coast, it's very flat. That being said, the waves are only very rarely ever going to come in exactly straight. Usually there'll still be a little bit of an angle to them when they hit. And as a result, they are going to move that sand up the beach a little bit, right? They hit the beach and their motion is sort of oblique to the beach. And the water slows down and it runs pretty much straight down the beach face under the force of gravity. So the swash ends up being a little bit oblique and the backwash ends up being pretty straight. And the swash is oblique and the backwash is pretty straight. And as a result, a particle of sediment or a tennis ball that you lose in the ocean is going to migrate up the beach moving in the direction of what we call the longshore current. That longshore current is just the current that's generated because waves are approaching at an oblique angle. And that's because, the wind direction might be inconsistent, but, if it's between any of these directions, it's going to generate a longshore current that's moving upshore. And usually, at least over the course of many months and years, that longshore current is going to be in the same direction on a given shoreline. So you can figure out which direction that longshore current is usually moving, because it's the direction that the winds are usually moving nearby. So the longshore current is generated by the wave motion and refraction at the shoreline, which in turn is generated by the wind. It's the ultimate source of that longshore current. Here you see just another view of that. Prevailing wind is this way. And so we know that there will be some refraction as it gets towards shore, but not complete. So there's swash and the backwash end up being not perfectly parallel to one another, which causes the longshore drift of particles up the beach due to that longshore current. Longshore drift is the name of the particle motion. The longshore current is more properly the name of the water motion, but you may see them interchanged a little bit. One more feature that's worth talking about that can happen near beaches, and it's always worth talking about because it is a safety risk. These are rip currents. Rip currents are fast moving currents of water where you have particular, the waves are coming in some spots, but then there might be a particular spot on the bottom of the shoreline where the channel itself is a little deeper. And so it's much easier for water to feed back into that channel and rapidly flow out towards sea in a particular spot. And if you get stuck in one of these, it can be pretty horrifying because it feels like it's just going to rip you right out into the ocean. But the key is that the water is moving out in only a very confined area. So don't fight the current. Don't try to swim in if you ever get stuck in these. Swim parallel to shore, because you will pretty soon escape that rip current, and you'll be in an area where either somebody can come out and save you, or it's much easier then to swim back into shore because you don't have these rip currents pulling you outward. It's really easy to drown if you just try to fight the rip current, because they'll move at a speed that about equivalent to how fast the fastest swimmers can swim. So you really can't make any progress against it. Let's talk a little bit about the details of how this works. So first, waves are going to pile that water onto the beach. Slows the waves down, piles that water onto the beach, rides up. The water is always going to follow the path of least resistance back. The best places to that are, say, along that underwater channel that I had drawn on the last one, underwater channel here, or toward a gap in the sandbar, because oftentimes you'll have these sandbars just offshore that are very shallow, but if there's a break in that sandbar, that's the easiest place for that water to run back outward. So you may find them along jetties. You may be able to identify them from the air because you can see where the water is a little more quiet, the waves are not breaking right in this spot, but this is a place that the rip current would pull you right out if it could. Another effect that we want to talk about is the way that we had talked about, right, the headlands and the little pocket beaches that are next to it on some of these active shorelines. One feature of the way that the waves refract around these is that at that projecting part of the shore, the wave is actually going to bend toward that point and focus its energy on those points. And as a result, it increases the wave impact on that headland. And so it works really hard to erode right there. Those headlands are pretty, on a geologic timescale, they're transient features because they get worked on so hard by that erosion. And as a result, you'll do a lot more erosion right on the headland, and you can still do deposition of those pocket beaches behind them, because out here, the impact is far lessened compared to where it is on the headland. So we had seen that image before. These headlands are being very actively worked on by erosion. This one especially probably is getting worked on over here. And so those are quickly breaking down. And some of the sediment that gets broken off, eroded off of those headlands, is just going to end up in the pocket beach, depending on the direction of longshore current in this spot.